Hey Calc, we're trying to wrap up this lesson, and so we're walking through these steps on how to sketch a function, and this is really the final version, where we start by looking at the original function and we find intercepts. Something that you've done in the past in math, x-intercepts, y-intercepts, and then you look for asymptotes. So asymptotes would be like if you have the 1 over x minus 2, and you can make an undefined there by putting in 2. If x equals 2, then it's undefined, and it's most likely an asymptote. Then you can test the first derivative. We said that means you're looking for critical points, and that means making the original function, find derivative, set it equal to 0, and solve. Those are either going to be maxima, minima, or an area where it's non-differentiable. Everything like that can be helpful in sketching your graph. You can find maxima, minima using the first derivative, or the second derivative can help you too, because when you find zeros in the second derivative, point of inflections are located there. And if you plug in your critical points into the second derivative, whether they're positive or negative, tells you maximum or minimum, right? If you have positive, you have a minimum right there. If you are negative, you have a maximum right there. Okay, so those are the little faces that we practiced. Finally, testing end behavior, kind of tied to step 1. You are going to be checking out what's happening when the graph goes into infinity, into as far right as it can go, like x into infinity, and x into negative infinity on your graph. So what's happening as it's going this way? What's happening as it's going this way? Is it approaching a value? That means you're going to be finding a limit. The limit as x approaches both positive and negative infinity. So we'll get into a little of that in some of our graphs. This one, the first one we were doing, sketch y equals x cubed minus 12x. We were actually doing this one in class. And so let me move my face here. There we go. The first step, test the function. This means that we're going to take that function and we are going to try and set it equal to 0 and plug in 0 for y and solve, plug in 0 for x and solve. So that's how you find y-intercepts and x-intercepts. When you plug in the 0 for x, you find the y-intercepts. When you plug in the 0 for y, you find the x-intercepts, where it crosses the x-axis, where it crosses the y-axis. So we did this in class. We found 3 intercepts. And we also did the y-intercept. Plug in 0 for y, or plug in 0 for x, right here. Okay, and you get 0 as your result. If you plug in 0 into the original function, you get 0, 0 as the point. And so here we are with your 2 things we know about the function, the intercepts. And we said this is a cubic problem, so you're seeing it on the backboard behind me where we left off. We're like, you know what, it's probably going to go up and go down and go back up. That'd be my guess. And I think we got even a little further to know that. We looked at the first derivative, which is step 2. So step 2, come here, there we go. Step 2 is to test the first derivative, find critical points. So what do you do? Take first derivative, here it is, just took derivative of this, and set it equal to 0. Solve, and you can find x values, x equals 2, x equals negative 2, where critical values are happening. Critical values are either maximums, minimums, or sometimes they're where the original function is not differentiable, which could be an asymptote, which could be like a corner or a cusp. Remember our corners on graphs or our cusps on graphs, or it could be where the function goes completely vertical and the slope is undefined. So all of those could be a critical value. But in this problem, we plugged 2 and negative 2 back into the function to find back into the original function. So we took the criticals, put them back into the original function to find actual points here for where exactly on the graph are our critical points. And this is the results you get when you plug in 2 and negative 2 into the original function. And these guys can be plotted on our graph. And they could be maximums, minimums, or something else. So we just have to list them as critical points right now and move on. Second derivative. Before we go there, you could next make that chart that we've done before where negative 2 is here, positive 2 is here, and test values in between and see if you have maximums or minimums. You are welcome to. Or you could wait till you get to the second derivative, because the second derivative can find this too. So second derivative, here's the original. First derivative, here's second derivative right here. Second derivative is so simple that makes this pretty easy to figure out where we're concave up, concave down, therefore finding maximums and minimums. It's also really easy to find where we have a point of inflection, because when is 6x equal to 0? Well, when x equals 0, duh. So we have this 0 on a number line that we can draw. And we have two critical values that we could put on there. Sorry for the jump there. I thought it was just going to pop up my critical values. -2 and +2. We found out those are the critical values of this function. If we put them in there, we can find out if we put a -2 in, we have 6 times -2, which is going to be a negative value. And if we do 6 times 2, it's a positive value. So this tells me that we are concave down over here and concave up over here. Okay, but we said that these could be maximums or minimums. And if it's negative here, that's a maximum right there. Boop, boop, at the top. So that's max. Same could be said for the min over here. We got a minimum value right there. And so we've got a maximum and minimum on our function, and we know where it's concave up and concave down. And so it's kind of said down there. You can read through that or pause it if you need to. Let me move my head out of the way real quick so you got a chance to read it. Okay, but that is all of the information we have on this graph, so we can sketch it. So we did the sketch on the board behind me before we finished class yesterday. We were pretty far along. We hadn't looked at the concavity much, but now that we have, we can plot all this stuff on here and get a really good graph going. So intercepts, square roots there, you know, we can just figure out where they might be crossing. Oh, I was afraid of that. Where it might be crossing. Okay, we're going to cross at 0, 0 for the y-intercept. We have a critical value of 2, -16, which is just like down here somewhere. Positive 2, positive 2, -16, my bad. Positive 2 over here. Let's just say this is 2. -16 is probably somewhere around here. -2, probably too far, but we got a positive there. Okay, and then the curve has a minimum at 2, -16, so it's going to curve down like that. Maximum there, and then finish your sketch. We could check that end behavior, but we'll check that out later, probably on a separate video. But that's kind of what we're guessing. There's the actual. Pretty good. All right, let's do another one. So sketch the graph. So this graph is a quartic. It's got x to the power of 4, which means that when we try and find intercepts, this could get ugly. So try and find x-intercepts there, and you set it equal to 0, and you go, what next? And you reach for your graphing calculator, right? Well, that's actually typically what the test would do. This comes from a source that I've suggested from a few of you to use on the AP prep book that I recommended, and it flat out tells you sometimes that the good news is when the roots are really hard, you're either going to have a calculator or you're just not going to have to find them. Okay, because they really do want to focus on other stuff than finding roots. But finding y-intercept isn't too hard. Remember how we do that? Instead of setting the y equal to 0, we just put 0 in for all the x's. And so that's a pretty easy way to find your y-intercept. We're going to cross the y-axis at 1 from the looks of things, right? And if you put 1 back into, if you put 0 in for x and you get 1 as a result, you have the 0.01. So there you go. Okay, critical points. Critical points. Again, this function, when you take derivative, now it gets a little easier to factor, but it's still not pretty. You have to do some creative factoring here to get this one done. Let me show you the shortcut here so you can see it. There's a 2x in common in all three of these terms, so you take it out. But then you still have the 2 in front, which is not always fun. But you can think of it as I have to multiply to get a -2 on the back, and I have to multiply in the front to get 2. So a negative 1 and 2 to get negative 2, and a positive 2 and a positive 1 to get 2 in the front. And then you just test it to see if you make your 3 in the middle, if you have to adjust your pluses and minuses. And there's your answer there, that we've got 3 critical values. We can put a 0 in here and get 0. We can put in a 1/2. Yeah, 2x minus 1, if you set that equal to 0. X equals 1/2. And a negative 2. So those are our 3 critical values. Let me get always moving myself around here. Yep, there we go. So those are our 3 critical values. Okay? So next, what do? Plug those in and get your points. So plug them in. If you put 1/2 into the function, you get 13/16. If you put negative 2 into the function, you get a negative 7. If you put in 0, you get 1. So there are our 3 critical points that we can put on our graph. So that's plugging into the original function to find where they are. All right, then we have to figure out what are these critical points. Are they maximums, minimums? And second derivative will help us with that, as well as find point of inflection. So second derivative, keep going with your first derivative, derive again. This function's nice. It's not too complex. So we can set the derivative equal to 0 and solve. And this doesn't work out evenly, and it sometimes doesn't. And so what this text suggests you do, if you're stuck with a quadratic equation, you can use the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, and you can get your two points of inflection at 0.26 and negative 1.26. So this isn't a pretty function, but we are getting it done. We found 2 points of inflection. We found 3 critical points. And so we're kind of picturing this thing that's going to, if all 3 critical points are maximums or minimums, we have a minimum followed by a maximum followed by a minimum, and we've got those 3, and then we've got points of inflection that are happening in between. So it's kind of what we're maybe heading towards. So now we can plug critical values in. So our critical values, remember, we're at 0, 1/2, and negative 2. I'm kind of covering them up over here. Okay? And so they're saying, hey, put these into the second derivative now and see if they're positive or negative. Because if they're positive, we have a minimum. If they're negative, we have a maximum. And it also is helping us find concave up and concave down. So put 0 in, you get a negative 4. So you're concave down, and it's a maximum. Put 1/2 in, you get a positive 5. And so you're concave up there, and it's a minimum. And finally, put negative 2 in there, and you get a positive 20. So the curve is concave up there. So concave up followed by concave up. So it's not quite what I was thinking on my graph. Looks like we're going to have to do some careful sketching for this one. Okay, so we can now plot the graph. And if you think about what we have found so far, let's put some of that up here. The curve has a y-intercept. Curve has a y-intercept of 0, 1. So right across here. Okay. Critical points at 0, 1. 1/2, 113. So 1/2, 113. So like critical here, and then the negative 2, negative 7. So down here. So here's our criticals. Well, that's interesting. Okay. Then we have points of inflection, which were pretty ugly. And so I don't know those values off the top of my head. But if you're looking at our graph here, the sketch of that, let me go back and see what those values were. 0.2690 and negative 1.263. Okay. So you put all that together and get your points, and you end up with a graph like this. Okay, so little bit of work to get this one, but our points are matching pretty well. Our max and mins and our points of inflection.